All right, hi class. Today, rather than our usual lecture format, me writing out notes, I will be coding up the Ising model so that you have a numerical tool to use and to explore without approximation the physics of the Ising model. So I'm going to live do this. So let's go ahead and share my screen here. All right, let's get rid of that. Hopefully you can see all of this. So I've pulled up my terminal here, and I'm going to create a document, Ising220a.py. I'm going to write this program in Python. I'm going to do what you should not do and go ahead and import from the beginning all of the libraries at all once. And I'm going to open this up in a text editor so it's easier to see. Okay. All right, hopefully that's clear. Okay, so we're going to study the Ising model, and we're going to do this computationally. And what does that mean? It means that we need to tell the computer the metropolis algorithm and all of the associate variables that it needs to modify. So let's try to be good programmers and comment everything. This is an import of the relevant libraries. This will give us access to data structures like arrays and simple mathematical operations, like the exponential function, which we'll need. All right, now in the Ising model, there's a handful of variables that we know we will need to specify completely the model. So for example, we need to know how many spins there are. Let's do this in such a way that we specify the length of one of the sides such that our spin lattice, again, we're going to study this in 2 dimensions, will be n by n big. So let's define that container here. Let's call it spins, and it will be an array, which is has n by n elements. This is the syntax for defining an array with zeros in every row and column. So that's a container. We can fill that container by, say, putting them all up. In fact, we can do that in 2 steps, like so. Okay, so now this is one initial condition where all the spins are up. We'll revisit different initial conditions in a little bit. Okay. So that's the total number of spins. Let's actually be a little bit more precise. Let's say nx is the number of spins on one side such that n is nx times nx. So n will really be the total number of spins. Okay. All right. Well, that's the bare minimum. We've defined our lattice. We're going to work on a square lattice like we've been talking about largely in class and drawing. So we've now defined some initial condition. All the spins are up. We've told the computer how many spins there are. Now what else do we need to do? Well, there's a couple other parameters in the Ising model. There's a j, which will be some value. There's a temperature, but really temperature always ends up in this model with a factor of the Boltzmann constant. So it will behoove us to specify kBt as a whole. Let's call that 1, 2. And indeed, beta then just is 1 over kBt. Those are parameters we'll need. What else? We need external field. Let's go ahead and comment this. Here's our exchange coupling. Here's our external field. Boltzmann's constant times temperature. Okay, what else do we need? So if you remember our energy function, that was equal to minus J, a sum over spins, minus H, a sum over single spins. So that was the total energy function. I've specified H and J. I've specified the domain over which these spins exist. That's setting my lattice. What else do I need to do? So now comes some more algorithm-specific quantities we need to define. So for example, we need to say how many times are we going to go through this procedure of, how many Monte Carlo, one usually calls them sweeps, are you going to use in order to estimate properties? So let's call that sweeps. Let's set it arbitrarily to begin with as at 1,000. So what I mean by sweeps is I will count in number of trials in spin flip attempts as one sweep. So the number of total spin flips is equal to n times the number of sweeps. Okay. All right. I think that's it. We've said how many times we're going to try to do this Monte Carlo procedure. We've defined the model and given an initial condition. We're really all ready. So let's count T as the index for what sweep we are on. Oh, let's do S, that's even better. For S in range sweeps. So that will give me a sweeps length number of loops. I want to take my spins, which I believe I called with an S, make this a little smaller so we can fit some of this stuff all on one thing, spins. I want to run it through a Monte Carlo algorithm. So I will give it this initial condition. I will ask the Monte Carlo procedure to update the spins, to resample them, and return that updated spin field. I'm going to do this S spin flip times. And now is a question of what sorts of things might I be interested in computing. For example, I might want to know the magnetization given some arrangement of spins, and it's a simple calculation to do. I just need to sum all the spins. If I want to be per n magnetization, I divide by n. And now I might want to print out, say what sweep I'm on and what that magnetization is. Okay, so we've got everything set up. Now is the real meat of the algorithm. We need to define a function which performs this Metropolis Monte Carlo random walk that we discussed in the last lecture. So let's define a function which is Monte Carlo that takes in the spins. And what does it need to do? Well, our algorithm was to first pick a random spin, second attempt to flip it, Those were the attempt probabilities, the attempt part of the Markov chain, the Monte Carlo algorithm. And then with a metropolis acceptance, having computed the energy, decide whether or not we accept that proposed move. So I'm going to define this Monte Carlo function as flipping through and trying to draw in separate spin flip moves. So I will, on average, try to flip every spin once. And now I need to draw a random spin. So how can I do that? So first, I'm going to need to import a pseudo random number generator. Like so. That's another relevant library. It lets me ask the computer to give me a random number. Let's call the x position of the random spin I. And let's say I want to generate a random number. This is the default random number generator in Python is between 0 and 1. I can make that a random number between 0 and nx by multiplying by nx. Except for now, this will be a number not necessarily defined on the integers. It's a continuous value. So I can make it an integer like so. So this is now a routine. Draws a random spin along x. I could do the same along y. And now I have a spin in both its row and its column that I will try to flip. Let's go ahead and name these a little bit better, x and y. And this is the one along y. So I've picked the random spin. Now I can go through the procedure of deciding whether or not, how I can flip it and whether or not I should accept that proposed spin flip. Before I do, I want to convince you that this will indeed generate a random spin between 0 and nx, and that distribution is uniform. So that attempt probability really is a constant equal for every spin. So let's go ahead and demonstrate that. Okay, let's imagine I had 10 spins on one side. I can make a histogram, an array, which will tell me, which will store which random spin I've picked. All right, and now let's try drawing 1,000 random positions along that x direction. And now I am claiming that this little procedure, taking the integer value of a random uniform number multiplied by nx, will on average draw numbers between 0 and 9, or nx minus 1, uniformly. So let's store some random value between what I'm claiming to be 0 and nx minus 1. Let's draw 1,000 of those. Quick to do. I can make a histogram of those values and showing it to you. Well, so there's 0 to 9. There's some deviations in that histogram. It's not super clear that 0 is being drawn just as often as, say, 3. If I draw 10 times as many random numbers, clear out that initial array. Drop 10 times as many numbers, save them. Okay, there we go. Let's see, that should look a whole lot flatter. And now you can maybe be convinced that there are just statistical fluctuations around what is in the long large number of random number limit, something uniform. Okay, so indeed, this little function will draw a random point on the lattice in the y direction and the x direction. Okay, so now I'm going to break this function up into, this part is essentially the proposal part, or part of the proposal part. And a metropolis acceptance routine. Okay. So this will take in that spin field, the random position in x and y that I've drawn to try to flip a spin, and if accepted, return a new spin field. If rejected, return their old spin field. So let's define a new function, the metropolis function. And now what do I need to do? So for this tagged spin, whose components, x and y, tell me where it is, I'm going to need to compute its energy. To compute its energy, I need to know its neighbors. The energy function, as we wrote down a second ago, is a sum over those nearest neighbors. So I'm going to define those neighbors as, if I look at a tag spin, I can either have a neighbor above me or below me, to my right or to my left. So let's call top the value of the spin at x, y plus 1. That'll take the spin that I've selected to try to flip and look right above it. I can do the same by defining the bottom spin and subtracting 1 off. I can look to the left, in which case I subtract 1 off of the x direction, and I can look to the right by adding 1 to the value of x. So those are my 4 neighbors. Those should, with the tag spin, uniquely determine the energy and how it changes when I attempt to flip the spin. All right, so there's one little trick here, however, which is that imagine the spin that I flipped, or that I've picked, the value of y, is right there on the edge. Say it's along the top. Looking 1 up depends on what the value of that spin up is, right above me, depends on what I'm going to use for my boundary conditions. So if this was a finite slab of a lattice, in which case the topmost spin was really the end of all the spins, I would just not have a neighbor to the top. However, such a setup would not be a high fidelity representation of a bulk system which we're trying to describe. So in fact, we want to employ something called periodic boundary conditions, PBC for what the cool kids say, in which case if I'm on the top row and I look up, that spin right above it is actually the spin on the bottom row, so that I loop back around periodically and the topmost spin sees the bottommost spins, or the bottommost spin sees the topmost spins as their lower neighbor. So I can rotate that back into the existing lattice with a modulus function. So let's see how that works. Imagine I have an x of 10, and I ask for spin 9 plus 1. Now, if I have 10 spins along the x, I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I only index up to 9 because I start at 0. So if I look at the neighbor above, spin number 9, if I mod that out by nx, that should give me 0, and indeed it does. How about if I was at 0 and I tried to look down? That should flip me back up to the top, so this should return 9, and indeed it does. Okay, so this is a nice compact way to engineer periodic boundary conditions that we can apply everywhere. Okay, so I've got my spins. Now I need to compute the energy, or more precisely, the change in the energy, delta E. So delta E is going to be minus J, the new value of the spin, so minus the spin that I've selected, X and Y, times up the one above me, the one below me, the one to my left, and the one to my right. Minus the flipped value of the spin times H, the external field. That's the new energy. The original energy was all of those with the original spin. Now notice, by flipping the spin, all I'm doing is changing the sign of this existing spin. If I move those signs everywhere, so this minus cancels out that minus cancels out that minus, this minus cancels out that minus, and that minus was all the way out here and cancels out that minus. I've actually just got 2 copies of the same thing. So there's a very simple expression for the change in the energy given a spin flip. It multiplies the spin that I'm trying to flip, the sum of its neighbors, and it should be twice H. So I can make this a little more compact. Like so. And just to make sure Python's not going to try to interpret those as integers and screw things up, let's give it little periods. Okay, so that's the change in the energy. All right, now Metropolis told us that we should accept that spin flip with probability. So if I draw a uniform random number and it is less than exponential of minus beta times delta E, then I should accept that spin, which accepting means to take the spin that I've picked, spins at X and Y and flip it. So its value goes to minus what it was before. And then I want to return the spins. So if it isn't accepted, if it doesn't enter this if statement, that spin will stay as it was, which is what we want. Okay. So that's the Metropolis acceptance criteria. So it will try to flip a spin. Only if this is true will it flip. Otherwise, it will return the original spins. This will be now a new set of spins, potentially, that it will then try to go through n times to try to flip n spins. Once it's exit out of that n attempts, I want to return the spins again. Okay. So we've got the Monte Carlo walk, the proposal, and the acceptance all put together. That's inside our main loop. Holy Moses, this is already all done, right? Does it work? Well, what can we do to check it? So what do we know? We know if these were actually the conditions I'm running under, I have some number of spins, I start all up, at J is 1 and KBT is 1, that's below the critical point, because the critical point in the two-dimensional Ising model from Onsager is T is equal to 2.26 J over KB. So at 1, it should be in the ordered state. So we can check it by running this code and seeing, as we print out the magnetization, that it stays near 1. That's where we start. Any chance that this is going to work? Very, very unlikely. I'm sure I've messed something up. Hey, that shouldn't happen. That actually scares me that nothing was wrong. Something probably should have gone wrong. Okay, well, this was the sweep number, and that was the spin. And it sure stayed near 1. Is this luck? What if we started all down? It should stay all down. Let's see if we go back up. It fluctuated. Something did happen, but it stayed, by and large, down. Now that happens, that runs pretty quickly. We don't actually, unless your eyes are really good, we don't really know what those fluctuations look like. So maybe instantaneous value of magnetization is not so useful. We probably want to compute averages. So let's actually define a container for the magnetization, like so. So that this is some big vector that gets added up, it gets stored, it stores the value of the magnetization, every one of these sweeps, like so. In which case we can print out not only the instantaneous value of the magnetization, but also its average. There's a real simple way to do that in Python, just mean. That's the mean function that computes its average. Okay, let's see if that really still holds true. Oh, goodness. I need only one of those. Here we go. Okay, so not only is the instantaneous value hovering near 1, but its average really does stick close to 1. Okay. What else do we know? Let's actually clean this up. Let's print that out in a little bit less precision. There we go. Even that's probably too much. Okay, what else do we know? So this was the behavior if we went to low temperature. We can all just as easily define J over KB as 1 and then manipulate the temperature directly. So we know that if the critical point is 2.26 J over KB, if we went to temperature 3, we should expect the magnetization to vanish. Let's see if that happens. J divided by KB. Oof, no, I'm messing everything up. Okay, let's not do that little switch. Hey, look at that. Instantaneously, we have some fluctuations, but the average sure looks like it's getting pretty small. But now we have a real question. Have we run long enough? Let's see if we run a little bit longer, how much that average goes to 0. Small, but not really small. We probably actually want to be able to plot this and see how it's decaying. We also are printing out every sweep. There's not a lot that can happen between 2 adjacent sweeps, so that's probably being printed out too often. So let's define a stat variable which tells us how often we print stuff out. We could use the same mod function if it is a multiple of stat, such that when modded it goes to 0, then and only then will I print that out. Okay, here's the plot function. Whoop. Hey, it really is just fluctuating around 0, though the fluctuations are pretty big. Let's clean this up a little bit, give it some good labels. So that is the magnetization. This is the time in number of sweeps. Let's see if we go back to low temperature, that it really does fluctuate around all up. Hey, sure enough, there are only really seldom departures from all up or all down, or from all up. In fact, that's an interesting point. What if we started all up and applied a negative field to bias it down? We haven't actually checked that. So let's say we apply some field. This should push an all up down. Didn't happen. Why is that? What if we try it again? It's random. Maybe this time it happens. Stays up. What if we jack up the field a little bit more? Yeah, now it went from all up to all down. So indeed, if you remember what our free energy looks like, there's a big barrier to going from all up to all down. You need a large enough field to destabilize that all up state and then make it favorable to go all down. That barrier probably gets a lot lower at higher temperature. So if we went a little bit closer to the critical point, even that small field, I bet will flip it up. Indeed, we immediately get small values. Okay, well, I bet I know what you all are thinking. What if we actually looked at the critical point? We're going to see anything interesting? So that's 2.26, call it 2.3. Hey, look at that. There are all sorts of fluctuations. The fluctuations are massive. It seems like it goes in between two stable states. What if we go a little bit higher? Wow, look at that. Fluctuations are enormous near the critical point. All right. It actually looks like it's working. What else should we do? Well, let's see. I bet you'd probably like to see what this actually looks like, huh? So maybe we should add in a little visualizer so we can actually look at what the spins look like. Let's make it a little bit bigger. Now I have cheated and worked that little function out ahead of time because that's a little complicated. Let's define some image flag. We'll set up a animating plot that will sequence through our spins, showing it how it updates. We need that function and this function. It'll probably be a lot to try to update it every time, so let's only update it every one of these stat variables, and let's increase that a little bit. Okay, let's go back to a slightly, okay, we're at a lower temperature. I'm going to start with an initial condition where all of them are up, except for the one in the corner. Whoop. Ah. Wow, cold temperature really is very boring, huh? Not a lot happening. It's like watching paint dry. That's not very interesting. All right, let's go to higher temperature and see what happens there. Hey, that's more interesting. That's temperature 3. That's lots up and lots of down. Though if my eyes do deceive me, it sure looks like they kind of clump together. Ah, but that's right. The correlation length is actually quite large as long as we're close to the critical temperature. If we went to even higher temperature, say something crazy like 5, what does that look like? My eye still looks like they're pretty clumpy. Sounds like maybe something you all should do is compute correlation lengths to actually see how localized those excitations are. Ooh, right. What else can we do here? You want to look at the critical point? Let's look at the critical point. Fluctuations on all sizes. Sometimes they're really big, sometimes they're really small, and they interconvert incredibly quickly. Not as impressive on such a small scale. How big can we go? Maybe 50? I suspect this is gonna, yeah. That's looking a little more interesting, huh? That's near the critical point. There really are all sorts of different size fluctuations. The fan on my computer is really acting up. It's not really liking me right now. Okay, so that's what that looks like. Oh, I have a neat idea. What if we start with an initial condition at coexistence? So let's start all spins up except for nx divided by 2, half of them being down. And let's do this first at cold temperature. Coexistence should be stable. Yeah, look at that. That interface wobbles around a little bit. Sometimes there are greens in the blue region. Sometimes there are blues in the green regions. That interface continues. What if we went to really cold temperature? We're going to see anything. Nothing. That's really boring. Oh, there's a fluctuation. Oh, it's kind of interesting. Not a lot going on there. All right, what if we went to slightly higher temperature? Wow, that interface gets real disordered. Fluctuations are pretty big, pretty close to the critical point. Whoa, so big that it destroyed the interface. Look at that. No, is it going to reform? There's no reason to say that it can't go away, and it looks like it did. That's cool. All right. What else can we do here? So, a very good test for whether or not any of this is reasonable is to try to recreate that equation of state, how the magnetization actually does go away at different temperatures. Will that be easy to do? Maybe I should let you all do that. Okay, well, we have our image. There's one last thing that I can do, which is to try to make this go a little bit faster. And so not all of you might have access to this library number. That makes these sorts of things go like a rocket. It essentially takes this Python code, which is interpreted on the fly, and turns it into compiled code, which is then run. It essentially translates all of this Python into C code. And that books it. Look at that. That's pretty quick, huh? Okay. So let's see. Anything else to discuss? We've got our Ising model, walk through how it's written. We've got our little image, so there are bells and whistles. Even have a little plotting function. I guess in lecture we did talk about actually considering what the histogram of the magnetization looks like, the probability of the magnetization. Let's maybe take a look at one of those. Let's do it at not so cold temperature, something like that, maybe. So rather than a plot of the time series of the magnetization, we'll look at a histogram of it. Hey, that's kind of nifty. So starting in all up, we get a peak near all up. It's not, though, exactly all up. There's some fluctuations. What if we start all down? Should look the same, right? Yeah, pretty similar. How about if we go to slightly higher temperature? Distribution's getting a little bit of a tail there. Let's maybe run it a little bit longer, see if we can get something interesting to happen. Hey, now this is getting pretty wonky and probably pretty hard to converge. Okay, so that's the histogram. Let's get one more just for good measure. Hey, now we're starting to even see two peaks. Okay, well, there you have it. Metropolis Monte Carlo made easy with Python and Xcode for visualization. There you have it. Okay, so I think this is actually in a state that I can just give it to you Thursday morning. You can play around with it. I'll take a couple pieces out to make you work on it a little bit. But the upcoming problem set that will be posted, let's see. So you have a new problem set for this week. It will be posted next Tuesday, and you'll essentially have a couple weeks to work on it. It won't be due until the end of our week. Okay, that's really all I've got. So short lecture today, different sorts of format. I hope you enjoyed it. Come with any questions in the live session, and I'll look forward to seeing you then.